In this module, we'll be going through how to calculate flexural stresses using the Force-in-the-Tendon approach. By the end of this module, I want you to be able to apply the given ACI 318 stress limits properly, calculate all required section properties, illustrate critical locations to check stress at different stages of the member's life, list stages of the member's life when stresses must be checked and should be checked, calculate stress in a given section under known loads at different stages of the member's life using the Force-in-the-Tendon approach. Force-in-the-Tendon approach also requires the use of pre-stress losses. So I want you to be able to calculate pre-stress losses using simple pre-stress loss procedures. List the stages of the member's life when deflections should be checked. Calculate deflections in members at the important stages of the member's life using the Force-in-the-Tendon approach, and to apply the given ACI 318-19 deflection limits properly. As we saw from Module 6, there are two main ways that we can calculate stresses. The first, which we talked about in Module 6, is the strain compatibility approach, where we calculate the strain at the centroid and the curvature in the section, and then from that calculate the strains and stresses at any location in the section depth. In this module, we're going to talk about the Force-in-the-Tendon approach. With this approach, we will assume that the pre-stressing force is an applied force on the section, and then we'll calculate the axial stresses, the flexural stresses from the pre-stressing, and flexural stresses from any external applied load, and then sum those to determine the stress at the top and the bottom of our section. With the Force-in-the-Tendon approach, we will assume that our pre-stressing acts as an applied force on our section at some eccentricity, the distance between the centroid of the section and the centroid of the strands. We can then use our basic mechanics relationships for our axial and our flexural stresses to determine the stress at the extreme fibers and also the stress at the pre-stressing strand location. The force applied by the pre-stressing strands is going to decrease over time because of creep shrinkage and strand relaxation. So here you can see an approximation of the strand stress plotted versus time, and you can see the initial stress that you put in at time of jacking is going to decrease over time. So we need to be able to account for this decrease in the pre-stressing force, and we'll do this using pre-stress losses. Our permissible stresses are going to be the same as those covered in Module 6 and as are summarized in the tables. So you can see here some of the primary concrete stress limits at release and at transfer. So our compression and tension limits at the end of simply supported members, so within that transfer length that we talked about, and also in all other locations, so at midspan or towards midspan. We also have our concrete stress limits at service. Here it's differentiated based on the type of the load. So if we have a pre-stress plus the sustained load, or our stresses due to pre-stress plus sustained load, we only have a compression limit as shown here. And if we have the pre-stress plus the total load, we have both a compression limit and a tension limit to make sure that our beam doesn't crack. Some of the critical sections at different stages are summarized on this slide and the next slide. Here are some of the critical sections at initial stage or at release or transfer. Typically, the stresses in the end of the beam, so tensile stresses in the top of the beam and compression stresses at the bottom of the beam, will control at release or transfer. So these will be the ones of most interest when we're checking our stresses. During our final stage or in service, our pre-stressing force is going to have its lowest value because of all the pre-stress losses, and our moment's going to have the highest value because we're including self-weight, superimposed dead load, and all of our live loads. So because of this, typically the tension stress on the bottom face of the beam at midspan is going to control, but we still need to check all of our top fiber and bottom fiber stresses along the length of the beam to satisfy our design. There are many different types of section properties that we can use with our Force-in-the-Tendon approach. The simplest is going to be just to use our gross section properties. And this, we disregard our pre-stressing and our steel areas, and we just use the gross section when calculating our section properties. The next approach is to use net and transform section properties. And with this, this procedure, which I'll talk about on later slides, is recommended by Collins and Mitchell in their textbook. The third type of section properties that we can use, or set of section properties that we can use, are the transformed section properties. And these we can use only if we don't take off the elastic shortening loss. And this method's recommended by Lynn and Burns in their textbook, and it's also used in several of the examples from the PCI Bridge Design Manual. The gross section approach is going to be the simplest, but it will typically give you some higher stresses. So if you use a more detailed approach, you can sometimes decrease your calculated stresses slightly. As I mentioned on the previous slide, the net and transform section properties are recommended to be used with the Force-in-the-Tendon approach by Collins and Mitchell in their textbook. These the net section properties should be used for any self-equilibrating forces. These include the pre-stressing forces and the self-weight of the member. So you use net sections for any self-equilibrating forces. The net section can be found by removing the area of the pre-stressing strands from your concrete area and by transforming the non-pre-stressed steel. So because you're transforming the non-pre-stressed steel, you can have both net short-term and net long-term transform section properties. So you can see some basic equations here. If you don't have any non-pre-stressed steel, then your net short-term will equal your net long-term properties. When using net and transform section properties, we're going to use our transform section properties to resist any externally applied loads. So superimposed dead loads or live loads will be resisted by our transform section. With our transform section, we're transforming our pre-stressing and our non-pre-stressed steel both into equivalent concrete areas using our modular ratio -1 times the area of pre-stressing and modular ratio of non-pre-stressed steel -1 times the area of steel. We want to calculate short-term and long-term transform section properties. The short-term transform section properties we'll use to resist live loads or any immediate loads. And long-term transform section properties we'll use to resist any sustained loads, so primarily superimposed dead loads. Lynn and Burns in their textbook and the PCI Bridge Design Manual examples recommend using transform section properties for all stress calculations. In this case, we're only going to calculate our short-term transform section properties. Typically, we may need to calculate these at release using our release concrete strength and at ultimate using our ultimate concrete strength. And then we'll also need to calculate our long-term transform section properties using our ultimate concrete strength and our effective modulus of elasticity for our concrete and pre-stressing. So here we'll have two sets of equations, and we'll need to use them to resist our loads based on if they're short-term loads at release or short-term or sustained loads when the beam's in service. Note that when we're using only transform section properties, we won't remove elastic shortening losses from our pre-stressing force. So when we're using transform section properties, we'll only remove our long-term losses from creep, shrinkage, and strand relaxation. When we use the Force-in-the-Tendon approach, we account for all of our time effects using pre-stress losses. So we need to calculate our pre-stress losses in order to figure out the force in the tendon at different points in the beam's life. There are many different ways that we can estimate pre-stress losses. There's a large variability in estimating anything related to concrete time effects. So typically a simpler approach is okay. The primary categories of loss estimation include lump sum methods, where you just assume a lump sum for different loss components. There are more detailed procedures and also more complicated time-dependent procedures. The primary types of losses that we'll include are from elastic shortening that happen immediately at release or transfer, creep loss due to the creep of the concrete, shrinkage loss due to the shrinkage of the concrete, and relaxation loss, which happens because of the relaxation of the pre-stressing strands. There's no ACI method for calculating losses, but there is an ACI 423 guide document for pre-stress losses that's available to help explain losses and how to estimate them. And the procedure that we'll use in this class, or the basic procedure we'll use, is from the PCI Design Handbook. In the PCI Design Handbook, we calculate the elastic shortening loss, the creep loss, shrinkage loss, and relaxation loss. Shown here are the equations for how to calculate the elastic shortening loss. The first thing we'll need to do is figure out the force in the pre-stressing before transfer, before release, and we apply that force to our section and calculate the stress at the centroid of our pre-stressing strands. This stress is going to drive our elastic shortening loss, or the shortening of our concrete section. So we take this stress times the ratio of our pre-stressing strands divided by our release modulus to get our elastic shortening loss. And then we can calculate the stress in the strand immediately after transfer by taking the stress in the strand before transfer minus the elastic shortening loss. As we saw earlier in class, concrete will creep or it will deform under sustained loads, and this deformation is going to decrease the effectiveness of our pre-stressing strands. We can account for this in the Force-in-the-Tendon approach by removing our pre-stress loss due to creep, and we can calculate it using the PCI Design Handbook approach using the equations on this slide. You can see here the creep loss is a factor of the stress that we calculated from elastic shortening and any stresses that are caused by the superimposed sustained loads at the centroid of the pre-stressing strand. So we can calculate this value used here. There will also be a volumetric change in the concrete that is caused by the shrinkage of the concrete. So we can calculate our shrinkage loss by taking the shrinkage strain times the modulus for our pre-stressing. And the PCI Design Handbook approach provides this simple equation here to calculate our shrinkage strain based on the volume to surface area ratio, which tells us how easy it is for water to leave the beam, and the relative humidity, which tells us how much the water wants to leave the beam. So a lower relative humidity, more water wants to leave than a higher relative humidity where the water is doesn't want to leave as much. So we calculate our shrinkage strain, take it times our modulus here for our pre-stressing strand, and that gives us our pre-stress loss due to shrinkage. We can calculate our pre-stress loss due to strand relaxation using the equation shown on this slide. Typically, we'll have grade 270 low relaxation strands. So using the table here from the PCI Design Handbook, we can find a K relaxation equal to 5,000 PSI and a J of 0.04. We then need to find the ratio of our initial pre-stressing stress, which typically is 202.5, to our ultimate strength of our strand, typically 270. So that ratio is typically going to be 0.75, and we'll typically have stress relief strands, low relaxation strands. So we'll have a factor C here of 1.0. We can add up all of our losses, so our elastic shortening loss, our shrinkage loss, our creep loss, and our relaxation loss to get our total pre-stress losses. And we can take the stress in our strand before transfer minus our elastic shortening to give the stress after transfer or after elastic shortening. And similarly, we can take the initial stress prior to transfer minus the total pre-stress loss to get the final stress in the strand after all of our pre-stress losses. We can take these stresses times our area to get the force in the pre-stressing strand after elastic shortening and after all of our losses. ACI 423, the document on pre-stress losses, highlights that transformed section properties can be used to directly solve for stresses in the concrete at the time of release, using our strand stress before transfer. So we can calculate our elastic shortening loss just by taking the strand stress before transfer with our transformed section properties. So using these equations here. And you can see the ACI 423 document that I show here, the guide to estimating pre-stress losses, for more details on this. There are three main times when we need to check our stresses. We need to check them at release or transfer. We need to check them under our sustained loads only, so our pre-stressing, our self-weight, and any superimposed dead loads. And then we also need to check them under all of our service loads, so under our pre-stressing, self-weight, superimposed dead loads, and our live loads. We can use any of the sets of section properties that we looked at earlier in the presentation so far, but typically using our gross section properties will be sufficient for our design. There's a significant variability in our material properties and our pre-stress loss calculations, which will typically negate any added benefit of using our net and/or transform section properties. Note that my sign convention throughout this presentation and the example problems is compression is negative and tension is positive. I'm going to present you with a couple different equations on the next couple slides. And I just wanted to note that you can use these equations along the length by changing the strand eccentricity if you have harping, strand area if you have debonding, and also the moments will change along the length. So those will be the values that you need to update. You do need to make sure that your stresses check along the entire member length. So typically, if we're doing this by hand, we may just check at the end or transfer length and at midspan. But if we have harp strands or debonded strands, the stresses may control somewhere between the transfer length and midspan. So you may need to, or you should check at other locations. If we're doing hand calculations, then 0.4L is a good place to check. And the equations shown below include typical components, but you can also add other components for additional moments or axial loads as needed for more complex cases. Shown here are the equations to calculate our stresses at release using our gross section properties and our transformed and net section properties. Here you can see that we have a negative axial stress applied from our pre-stressing, so negative P over A. In the top fiber, the eccentricity of our strands is going to cause compression in the bottom and tension in the top. So we'll have a positive value here, so positive PE Y over I. And our moments are going to cause compression in the top and tension in the bottom. So we'll have a negative sign here, negative MY over I. So our bottom fiber, our axial stress is still compression. Like I said, the flexural stress from our strand eccentricity will be compression in the bottom fiber, so minus here. And our applied moments are going to cause tension in the bottom, so we have a plus MY over I component here. For our transformed and net section properties, remember that we'll use our net section properties to resist any self-equilibrating forces, which are the pre-stressing forces and our self-weight moment. So here, if we're looking at release, we use our net section properties. And we want to make sure that we use our net section properties at release. So if we have any non-pre-stressed steel, we want to transform it using our release strength of our concrete. The equations that we can use to calculate our stresses due to our sustained loads are shown on this slide for gross section and transformed section properties. Note here, it's a similar equations, same signs, except we now use the pre-stressing force at final after all pre-stress losses, and we're including an additional flexural stress component that accounts for any moments due to our superimposed dead loads. You can see here we still use our net section properties for our self-equilibrating forces, except now we're going to use our long-term net section properties. So if we have any non-pre-stressed steel, we'll transform it using our effective modulus for our steel and our concrete. So I mean, typically you'll just use ES divided by EC effective for that. With the superimposed dead loads, it's an externally applied load. So we'll use our long-term transform section properties to calculate our stresses due to those. Finally, we can calculate our stresses due to all of our service loads. So here are our equations for gross section and our transformed and net section properties. With our gross section, we have the same 4 components that we did for our sustained loads, but now we're adding an additional component for all of our moments, or our stresses due to our live loads. So this is an additional component to what we had on the previous slide. With our transform and net section properties, we again have the same 4 components from our sustained loads. And now we're adding in the last component here for our flexural stresses from our live loads. And you can see we're going to use our short-term transform section properties because our live loads are externally applied loads and they're immediate loads. So they're not sustained. So we use short-term transform section properties. At this point, you can pause this video and go to example problem 1, where we calculate the release stresses for the section shown using the 3 different section properties that we've talked about in the class. Next, you can go to the example problem 2, where we calculate the service stresses for the section shown here using the 3 different types of section properties that we've talked about. On the next few slides, I'm going to briefly go over the ACI 318 crack control reinforcement requirements. Typically, we're going to try to design our beam so that we have a class U beam, which means it'll remain uncracked through its service life. If we design a class U beam, we don't have any crack control reinforcement requirements, and we don't have any side skin reinforcement requirements. So this is the simplest, and this will be typically what we want to try to do. If we do have a cracked beam, a class C pre-stressed beam, then we do need to provide non-pre-stressed reinforcement or bonded reinforcement on our beam to resist the crack widths. So we would need to meet the spacing requirements shown in this table. This slide shows some of the definitions for the variables used in the table shown on the previous slide. And here's some last notes on the crack control reinforcement. Note again that this is only for class C beams, so typically you'll try to design a class U beam, so that's why I'm going through these so fast. On the next couple slides, we're going to talk about how to estimate and calculate our camber and deflections, and also look at some of the ACI 318-19 camber and deflection requirements. So you can see here a table, and our computed deflections must not exceed these specified limits from ACI 318. So you can see it's based, the deflection limits are based on the member type. So whether we have a flat roof or floor, or a roof or floor, the condition, so is it attached to or not attached to elements that are likely to be damaged due to large deflections, and then here the type of load that we use to calculate our deflections. So we're looking at immediate, or are we looking at all the loads that are applied after the member is placed in service? And then you see here the different deflection limitations. If we assume that we have linear elastic material properties and assume that our pre-stressing force is applied to the section in terms of a force, we can come up with these basic equations shown here that we'll use to calculate deflections. We have our deflection due to our uniform loads, so this will be any applied loads from our self-weight, our superimposed dead loads, our live loads. And then we have a different set equations to account for the deflections from our pre-stressing. If we have a constant eccentricity, we can use this first equation here. If we have a single harping point at midspan, we can use this equation here where we have a different eccentricity at the center of the beam than we do at the ends of the beam. If we have a double harping point, we can use this equation here. And if we have a parabolic strand profile, we can use this equation here to estimate our deflections. We need to somehow estimate our long-term deflections, so increased deflections that occur because of creep and shrinkage of the beam. And we can do this either by using our effective modulus, in which case we need to calculate our creep coefficient, or we can use the PCI Multiplier Approach that's shown on this slide and the next couple slides. So the PCI Multiplier Approach essentially requires you to calculate some base deflections, and then they have a multiplier that you take times that deflection to calculate the long-term effects or long-term deflection. The four base deflections are the deflection due to pre-stressing alone, deflection due to self-weight, and both these you want to calculate at release using the modulus of elasticity with the concrete or with the release strength of the concrete. Then we'll have the superimposed dead load deflection, and this will use the 28-day strength or the ultimate strength of our concrete. And then we'll also have our live load deflection. And with these four base deflections, we can then use a multiplier to calculate the deflections at time of construction or erection, and also the deflections at final time or when the beam's in service. If we have a straight strand profile and a distributed load, then our camber at erection and camber at final time can be calculated using these equations, which is just the deflection equation from a couple slides ago with the PCI multipliers. At this point, you can pause this video again and go to the accompanying video for example problem 3. On the next few slides, we're going to continue an example problem that we started in Module 6. In Module 6, we found the stresses for the section shown below using the strain compatibility approach. In this section, we're going to look at the stresses from the traditional force-in-the-tendon approach that we've been going through, and then we'll also bring in stresses from the layered section approach as a point of comparison. The section in this example is a single T with 14 half-inch diameter strands. And this example problem is based on a design example that was completed by Dr. Bayrak and Dickerson from the University of Texas at Austin. The beam in this example uses harped strands with a single harping point in the middle. So we'll have a different eccentricity of the strands at midspan than at the end. So we'll need to calculate the eccentricity of the strands at any section where we want to calculate our stresses. You can see also some of our information on our loads. We have our self-weight load, we have our span length of 80 feet, and we have our live load here and superimposed dead load. Shown here is the strand eccentricity at several points where we'll be calculating stresses. We'll be calculating stresses at our transfer length, at 40% length, and at midspan. And then here are our gross section properties and our total strand area. Shown here are some of our material properties. We have our concrete strength and modulus at release, and our concrete strength and modulus at 28 days using our ultimate strength. and then also some of the information on our pre-stressing strands, our ultimate strength, the initial strand stress, and our stiffness and modulus of the pre-stressing strands. Here are some reminders about the Force-in-the-Tendon approach. For the Force-in-the-Tendon approach, we need to make sure that we estimate our pre-stress losses at each stage of the service life under consideration. We can use either the gross section or net and or transform section properties. So in this example, we'll use gross section and we'll use net transform sections. We can use the superposition of all of our forces and moments to calculate our stresses and our deflections. The Force-in-the-Tendon approach is only valid in the elastic range of our material stresses. And it's easiest to use if we're using our gross section properties, as we'll see in the example. And also note that our losses are typically only calculated at midspan, and the pre-stress force is just assumed to be constant along the length of the beam. But this is just an approximation. Our first step is to calculate our elastic shortening loss. And I'm going to use two different procedures to calculate the elastic shortening loss. The first one shown here is from the PCI Design Handbook. So with this approach, we need to calculate the initial pre-stress force at the time of jacking before our pre-stress loss. We then calculate our self-weight moment, and we use our self-weight moment and the pre-stressing force to calculate the concrete stress at the centroid of our pre-stressing. Here we plug in all of our values for the stress at the centroid of the pre-stressing strands due to our pre-stressing and self-weight moment. And we'll get a stress here of 1.43 KSI. We take this times our pre-stressing modulus divided by our concrete modulus at release to get our elastic shortening loss of 12.3 KSI. A more exact approach for calculating our elastic shortening loss is shown on this slide from AASHTO. So you can see this equation, which is essentially a simplification of an iterative approach, which we'll talk about in a later module. But if we plug in all of our values here, we can get an elastic shortening loss of 13.4 KSI. Here again are some more details on that iterative approach. Again, you can see a loss here of 13.4 KSI. And since this procedure is typically more accurate, we're going to use this elastic shortening loss in this example. Next, we need to calculate our creep loss, or our loss due to creep of the concrete. And we'll use the equations from the PCI Design Handbook. We need to first calculate the stress from our superimposed sustain loads, and those will be caused by our moment from our sustained dead loads. And then we can use the stress that we calculated before at the centroid of our pre-stressing strands due to our pre-stressing force and our self-weight moment, minus this stress due to our superimposed dead loads, times our modulus of the pre-stressing divided by the modulus of the concrete considering the ultimate strength of the concrete, and get our creep loss here, 18.16 KSI. We can now calculate our shrinkage loss by calculating our shrinkage strain first. And to find our shrinkage strain, we need our volume to surface area ratio for a section, which is going to be about equal to the area of the section divided by the perimeter. So we were given these values, the area 570 square inches and the perimeter 254.6. So taking 570 divided by 254.6 gives us a volume to surface area ratio of 2.38. Our relative humidity was given for the location of the beam as 68%. So we can plug in these values, plugging in our volume to surface area ratio into our equation in units of inch. And then our 68%, we just plug in a 68 into this equation here. So we'll get a shrinkage strain of 0.225 times 10 to the negative third. And then we take this times our pre-stressing modulus to get our shrinkage loss of 6.59 KSI. Next, we can calculate our relaxation loss using the tables from the PCI Design Handbook. So you can go back to the slide from earlier in the presentation to look at those tables again, but plugging in our values, we'll get a relaxation loss of 3.47 KSI. If we add all of our losses together, we'll get a total pre-stress loss here of 41.62 KSI. For our stress calculations, we'll need to find our initial pre-stressing force after release or after transfer, and we'll also need to find our final pre-stressing force. For this, we just take our stress in the strand before transfer minus elastic shortening times our total area to get the force immediately after transfer. And for the final pre-stress, we take our force before transfer minus our total pre-stress loss to get our stress in the strand after all losses, and take that stress times our area to get our final pre-stressing force. We'll need to take the force times an eccentricity to get the moment caused by the eccentric strands. So we can do that here, or we can just do it in the equations later. But these values I give you here as well. Our first step here is we'll calculate all of our stresses due to using our gross section approximation. So we first need to find our stresses at release at the top and bottom fiber. So we can use these equations here. And plugging in all of our known values from the previous slides, we can find the stresses at the top and bottom fiber at midspan, at 40% length, and at transfer length. So I give you some of these numbers so you can check them yourself if you want. And we can see the final stress, which is of interest for us. We next need to find all of our stresses due to our sustained loads. So we'll have the same components that we did before, except now we use the force in the pre-stressing after all losses. And we're also including the flexural stresses from all of our superimposed dead loads. We can use the equations on the previous slide with the values from other previous slides to calculate our top and bottom fiber stresses at midspan, at 40% length, and at transfer length. And again, I give you some of these values so you can check these numbers if you want, but the stresses here on the right side are the ones of interest for us. Finally, we can calculate our stresses due to our service loads using our gross section. And we'll have the same first four components that we did from the sustained load check, but we'll also have the additional component here from our live load. So we can calculate our top and bottom fiber stresses using these equations. Plugging in all of our known values, we can calculate the stresses shown here on the right. And you can see our stresses at midspan and our tensile stress at 40% length both exceed the tensile stress limit here. So you can see if we're just using our gross sections, our stresses don't check against our code limits, so we would need to redesign our beam. Next, we're going to use or find our stresses using the net and transform section response. And to do this, we need to calculate our long-term material properties. For this, we'll need our volume to surface area ratio, which we found before. We'll need our relative humidity, which we were given. And we also need some information on our loading age. So we're going to assume that our initial loading age is 1 day, and that the time when we're interested in our long-term effects is going to be 10,000 days. We can use these values with the AASHTO LRFD 2004 approach to calculate our creep coefficient. So we can calculate our creep coefficient, and with this we need to calculate some different K factors, which I show you how to find here. Plugging in all of our known values, we can calculate our creep coefficient to be 2.5. With this creep coefficient, we need to calculate our effective modulus. And our effective modulus is just going to be our modulus of elasticity for our concrete divided by 1 plus our creep coefficient. So 4030 KSI divided by 1 plus 2.5 will give us an effective modulus here of 1150 KSI. We also need to find our pre-stressing steel relaxation. And again, we'll use an equation from the AASHTO LRFD 2004 approach to find that we'll have about 2% strand relaxation. So we can take this 0.98 times our strand modulus to get our effective modulus of 28,420 KSI. Using our gross section properties, our strand area, and the location of the strand, with all of our long-term effects that we calculated on the last few slides, we can calculate our net and short and long-term transform section properties. Shown here are the equations that we'll use to calculate our net section properties: our net area, our net centroid, and our net moment of inertia. We can plug in all of our known values from our mid-span section to find our net area, our net centroid, and net moment of inertia. But note that the net section properties are going to change along the length because we have harped strands, and the location of our pre-stressing is changing along the length. Shown here in this table are our net section properties at midspan, at 40% length, and at the transfer length. Note that we don't have any non-pre-stressed steel here, so our net section or our short-term and long-term net section properties are going to be equal. If we did have non-pre-stressed reinforcement, then we would need to transform our non-pre-stressed reinforcement when calculating our net section properties for short-term and long-term. On the next few slides, we'll calculate our short-term and long-term transform section properties. For our short-term transform section properties, we'll use our modular ratio with our pre-stressing and our modulus of elasticity without taking into account creep. And we can use the equations shown on this slide to calculate our transformed area, transformed centroid, and transformed moment of inertia. On this slide, we plug in all of our known values with our properties at midspan to calculate our transformed area, our short-term transformed area, our short-term transformed centroid, and our short-term transformed moment of inertia. We can do this for our three different sections where we're checking our stresses at midspan, at 40% length, and at the transfer length. When calculating our long-term transform section properties, we'll use the same equations that we did for our short-term, except we'll change our modular ratio. So here's our new modular ratio, which is the ratio of our effective modulus for our pre-stressing divided by the effective modulus for our concrete. So you can see here the modular ratio is going to change to 24.7 when we take into account creep and strand relaxation. Shown on this slide are the equations that we can use to calculate our long-term transformed area, our long-term transformed centroid, and our long-term transformed moment of inertia. And here again, we can plug in all of our known values at the midspan section to calculate these three values: the long-term transformed area, long-term transformed centroid, and long-term transformed moment of inertia. Finally, we need to calculate our long-term transform section properties at the three locations where we're going to check our stresses. Note that these properties are going to change in this example at the different locations because we have harped strands. If you have straight strands and you don't have any debonding, then your section properties will remain or will be the same along the length of the beam. Now that we've calculated all of our required net and transform section properties, we can now calculate our stresses using our using these net and transform sections. So here are the equations that we'll use to calculate our top and bottom fiber stresses. Note that when we're looking at release and when we're using our self-equilibrating forces, our pre-stressing and our self-weight, we want to use our net section properties here. So you can see we use our net area, net moment of inertia, and net eccentricity. and the distance between the top of the section and the centroid of our net section. So we can also use this equation here to calculate our bottom fiber stresses. We can use the equations on the previous slide with all of our known values to calculate our top and bottom fiber stresses at midspan, at 40% length, and at our transfer length. So these will be our stresses at release that we can use to check our stresses versus our code limits. We can use these equations then to calculate our stresses due to our sustained load. Note that, again, we have a difference here where we're using our pre-stress force after all of our losses to calculate the axial and flexural stresses from our pre-stressing. We're still using our net section properties to resist our self-equilibrating forces, our pre-stressing force and our self-weight stresses. And now we have an additional term here for the stresses from our superimposed dead loads or our sustained loads. And here, because it's an externally applied load and it's a sustained load, we'll use our long-term transform section properties. So you can see that component there, and then also we added on with our bottom fiber stress as well. Using the equations on the previous slide with all of our known values, we can calculate our top and bottom fiber stresses at our 3 points of interest. And we can compare these stresses against our ACI 318 stress checks for pre-stressing plus all of our sustained loads. Shown on this slide are the equations that we can use to calculate our stresses due to all of our service loads. We'll have all the same first 4 components that we did for our sustained loads, but now we'll have an additional component here for our stresses due to our live loads. And you can see a live load is an immediate load, and it's an external load. So we'll use our short-term transform section properties. Shown on this slide are all of our calculated stresses due to our service loads at our 3 locations. So you can see we still are exceeding our stresses at our 40% length, but the calculated stress is less than the stresses that we had with our gross section. Next, we can calculate all of our deflections. So we can calculate our initial camber and our final camber and our final service deflections. So shown here are our deflections due to our pre-stressing. And because we're looking at initial camber, we're going to use the modulus of elasticity using the release strength of our concrete. So E sub Ci here. We're going to use gross section properties here just for simplicity. And this will typically give you similar results to if you use net section properties. So here you can see the deflection from our pre-stressing is going to lead to 3.41 inches of an upward deflection. And then from our self-weight, again using E sub Ci, we can find a deflection of 2.38 inches downward. We can add these up to get our total deflection, or our total initial camber. And we'll have an initial camber here of negative 1.03, which will be an upward deflection. Shown on this slide is our deflection from our pre-stressing and all of our sustained loads, our self-weight and our superimposed dead load. If we're looking at final time, we're going to use EC effective. So we found EC effective earlier, so we'll just plug that in here. And we use EC effective when finding our deflections due to any sustained loads. So our pre-stressing is sustained, and our self-weight and our superimposed dead loads are sustained, so we'll use EC effective for all those loads. We can find our deflections here just by plugging in all of our known values and our gross section properties. We can also note that if we're looking at final time, we're going to use our pre-stress force after all of our pre-stress losses, so P sub F, so we plug in that there as well. And we can find an initial deflection due to our pre-stressing about 8.5 inches upward, and our deflection from our self-weight and our superimposed dead load is going to lead to about 8.14 inches of a downward deflection. If we add those together, we'll get a total deflection due to all of our pre-stressing and sustained loads of 0.33 inches, upward still, so upward deflection. And finally, we can find our deflections due to our live loads. Our live loads are immediate loads, and they'll happen at service, so when our concrete has reached its ultimate strength. So the modulus of elasticity for our concrete that we use is with our ultimate strength for our concrete. Plugging in our distributed live load and all of our known gross section properties and EC, we can find a downward deflection of 1.33 inches due to our live load. We can add this to our total deflection from all of our sustained loads and the pre-stressing to get a final service load deflection of about 1 inch downward. Our third option for calculating stresses is going to be using a layered section approach. This approach is much more complex. It's an approach that doesn't or uses exact stress-strain relationships for all of our materials, so it's valid both in and out of the elastic range. And it's about equivalent to the strain compatibility approach if we're in the linear elastic range. We talked in more depth about the layered section approach in Module 5, but just as a reminder, the layered section approach breaks up our section into concrete layers, steel layers, and pre-stressing layers. We would then find the strain at the centroid of each one of these layers, and then use our material or our stress-strain relationships to find the stress in each layer. So we would find an average concrete stress, an average pre-stressing stress, and an average non-pre-stressed steel stress in each of our layers. We can then just use our equilibrium equations to find the axial load and the moment due to the strain state and stress state in our layered section. As we saw in Module 5, Response 2000 is a freely available layered section analysis software. And using that, we can find our stresses at release, which are summarized in this table for our midspan, 0.4L, and transfer length locations. Shown on this slide is a summary of the stresses due to our sustained loads using our layered section approach. And here are the stresses due to all of our live loads from our layered section approach. We can add all of our stresses from our sustained loads to our stresses from our live loads to get the total stress in the top and bottom fiber and at the location of our pre-stressing. You can see here that now at 40% of the length, our tensile stress is now check. So using the more detailed approach allowed us to get our stresses to check in this section. On the next few slides, we'll look at a side-by-side comparison of our stresses found using our different approaches at our different sections and at the different times. So here, if we're looking at midspan at release, we can see our comparison between the traditional Force-in-the-Tendon approach using gross sections, Force-in-the-Tendon approach using our net and transform section properties, the strain compatibility approach, which we went over in Module 6, and the layered section approach, which we went over in Module 5. So you can see there are similar stresses here using our Force-in-the-Tendon strain compatibility approaches, and we have a slightly higher compression stress if we use the layered section approach here. On this slide, we look at our stresses due to our sustained loads at midspan using our different approaches. And you can see that the stresses are fairly similar between the 4 different approaches. Here are our stresses due to our service loads at midspan. And you can see here that we see the biggest difference here. So before, if we use the Force-in-the-Tendon approach with our gross section, then our bottom fiber stresses don't check at midspan. But if we use our Force-in-the-Tendon with our net and transform section properties, or if we use strain compatibility or our layered section approach, we'll get our stresses to check versus our ACI 318 code limit. Shown here are the stresses at 40% length at release. So we can see, again, comparable stresses using our 3 different hand calculations, but a slightly higher compressive stress using our layered section approach. Here are our stresses at 40% length due to sustained load, and again, they're fairly similar across using the different approaches. We have slightly higher compressive stress if we use strain compatibility or layered section. And shown here are the stresses at 40% length due to our service loads. And again, you can see the biggest difference here. If we use gross section or net and transform section approach with the Force-in-the-Tendon, our stresses would not check compared to our code limit. Even if we use strain compatibility, it's still close, but our stresses still wouldn't check. If we use our layered section approach, however, we can see that our stresses now check. So this is just a way that shows you that if your stresses are close to checking but don't quite check, you can use a more detailed approach to see if your stresses check, which would allow you to have an okay design without needing to add more steel or change your section shape. Finally, looking at our stresses at the transfer length at release, we can compare the 3 different hand calculation approaches and see similar to before, we'll get a slightly higher compressive strength using our layered section approach. We have similar compressive stress due to our sustained loads, as shown on this slide. And we'll also have similar compressive stress due to our service loads, as shown here. Finally, we can compare our midspan deflection using the Force-in-the-Tendon approach discussed in this module and the moment area theorem approach, which we discussed in Module 5 and then used in the Module 6 example. So you can see we have pretty similar initial camber. Our final camber starts to get a little off. Our deflection due to live loads are very similar, but because of that difference in final camber, our total service load deflection is about 0.6 inches difference. So the Force-in-the-Tendon approach it's a very reasonable approach to use to estimate deflections as long as you're staying in the linear elastic range. As soon as you go outside the linear elastic range, you need to use a more detailed approach to calculate your deflections, and one of them is the moment area theorem with your moment curvature diagrams. So that concludes this example problem. At this point, you can pause this video and you can go to the accompanying video for example problem 4, where we'll calculate the pre-stress loss using the PCI Design Handbook. We'll check stresses at midspan and at the beam ends using our gross section properties. And then finally, we'll also check our midspan deflections using our gross section properties and the PCI multiplier method. And we'll do all these for this standard double T section. That concludes this presentation on how to find flexural stresses using Force-in-the-Tendon approach.